Hello and welcome to my infrared astronomy channel. Today I'm going to show you some infrared astronomy satellites. It's just a selection of satellites that existed or still exist. This is the list. The reason why I had to redo this video is I forgot this very notable satellite at the end that is gonna start soon. One of the first dedicated infrared satellites was IRAS. You can see it here on the left hand side. It was running on a sun-synchronous orbit, so it had the same conditions all the time. And this is quite typical. You see the protection from the sun here, like a sunshade, and the opening of the telescope is skew in a way to block sunlight coming in. It was a 0.57 meter Ritchey Chretien telescope and had spectrometer and detectors on board that could tap a very wide range of infrared from 8 to 120 microns. And what the satellite did, it was a survey of the whole sky, and it made catalogs of 350,000 infrared sources. It worked for 11 months. Then the ISO, the Infrared Satellite Observatory, had its first light in 1995, and it was an ESA-managed satellite with a 0.6 meters telescope. It had cameras and polarimeter and also two spectrometers on board. The orbit was very special. It had a highly eccentric orbit going between 500 and 72,000 kilometers above the Earth, which one orbit took exactly 1 day, which made it easy to report the data once a day back to the Earth. It looked for water in the solar system and also looked at galaxies in the infrared, as you can see on the right hand side here with the example of M51 in Canis Venatici. Its service time was 3 years. Then Spitzer was dedicated to observing extrasolar planets, but it looked also at high redshift galaxies, and it worked for 16.5 years, but the cold phase was only 6 years. I mean, that's already quite long, actually. This is relatively typical for infrared satellites because they have to be cooled and the coolant will boil off over time, which limits their life, especially for long wave infrared. And then sometimes they have a warm phase where you still can use them for near or short wave infrared. Spitzer had a 0.85 meters mirror and was helium cooled. And you can see some of the example pictures on the right hand side, this planetary nebula and this galaxy. Galaxies tend to have lots of structure in the infrared because you can see through the dust. Then Akari, or ISAS, was a Japanese satellite that started working in 2006. And it had a 0.685 meters Ritchey Chretien telescope. It looked for supernovae and observed star formations, like one here in the galaxy M101. And compiling all the images from these satellites, you got something like this with the Milky Way here. It also had detectors that could tap the spectral range from 1.7 up to 180 microns. And it worked for 4.5 years, but was cold for 2.5 years, and then the rest of the time it was a warm satellite. Also here you can see the sunshade, and the solar cells are probably also used as a sunshade. That's why you have them a little bit away from the satellite too, for the radiation shouldn't be too strong on the satellite, the heat radiation I mean. Then the WISE satellite took pictures like this. This is color coded, of course, because there are no natural colors in infrared. It was a 0.5 meters mirror, which was cooled with solid hydrogen, which is quite a funny thing. I didn't know this was possible to have solid hydrogen, but it's very, very cold. WISE was observing minor planets and star clusters, and it got famous for discovering comet Neowise. Here, this is not comet Neowise actually, it's comet Siding Spring, but the picture was taken by WISE. Neowise was just the end phase of WISE when it got warm. It was there for 13 years and was in the cold phase for 4 years, and then it had a break, and only after a couple of years people thought this satellite is still up there, we could use it to look for near-Earth objects, and this was the Neowise phase of the WISE satellite. It had already quite high resolution detectors working with silicium and arsenic, and a longer wave detector with mercury cadmium tellur sensor. This is a very famous infrared satellite, James Webb. James Webb was built to look for early galaxies and also observe extrasolar planets. It was built by NASA and it cost billions of dollars, which started already with the mirror, which is very, very sophisticated. It's made out of beryllium, and beryllium is not really a material that is good for building mirrors, but they found a way to make it to a quality that can be used, and it has gold on the beryllium. And these 18 mirrors had to be tuned in, which took quite a while in the beginning before it could start observing. And it was started with an Ariane 5 rocket, with the second last Ariane 5 rocket, and put to the Lagrange 2 point, which is behind the Earth as seen from the Sun. And then it had to fold up, and the folding up was a very complicated process. As you can see here, it has 5 sunshades under it. And being in the Lagrange point and behind these sunshades means it can see half the sky in spring and the other half sky in autumn, depending on where the Earth is and where the satellite is, but it's actually circling the Sun and not the Earth. And it has a 6.5 meters mirror, which is a Korsch telescope, a 3 mirror anastigmat. with quite a long focal length. So it can't do service. It can observe single objects, small objects, like this red spider nebula here. The star shapes it produces are very unique. Not many telescopes do that. They're quite nice and like a signature on the image that you see. It's from James Webb telescope. And it also took high-resolution pictures of the planets, although it wasn't strictly built for that. And the high-resolution images are from the near cam, whereas the MIRI is looking for longer wave infrared, and there you can't do as high resolution images. And this is the most famous picture of James Webb telescope, which is Pillars of Creation, which is part of the nebula in the constellation Aquila. Then even more modern satellite is Euclid, which was put into service into 2023 by ESA but also NASA. And is also a Korsch telescope, but only with 1.2 meters diameter, and also quite a long wavelength, focal length. It's cooled also. I didn't find out exactly to what degree it is cooled, but certainly liquid nitrogen or colder. And it has both a visual camera and a near-infrared spectrometer, working between 0.55 and 2 microns. And is also on the Lagrange point 2. So it's almost a smaller version of the James Webb telescope. But its main purpose is to look for dark matter and dark energy. We don't know yet how long it's gonna work, but it should work for 6 years, people think. The Sphere X telescope is quite a special telescope that consists of 3 mirrors of 0.2 meters diameter, one inside the other. That's something you can see in X-ray satellites a lot, but for infrared satellites it's quite special. And the reason why people did that is they wanted to cool the mirrors too, not just the sensor. And its main purpose is to do galaxy spectroscopy, and it should do this for 450 million galaxies, which sounds almost impossible in the short time of a bit more than 2 years, but I hope it's gonna work. And it's looking for water in these galaxies. It wants to know how frequent water is in space. The sensor is a mercury cadmium tellur sensor with quite high resolution. Then a telescope that hasn't been started yet but will start quite soon and will start working in 2027 is the Nancy Grace Roman telescope by NASA. And it also uses a 3-mirror anastigmat, quite a large one with 2.4 meters diameter. And it has detectors for the visual and near infrared, and also coronagraph. So it will work to see extrasolar planets, but also dark energy. And it will also look for primordial black holes, which is a very interesting part of astrophysics. I can't say anything about its service time yet. So to give a short summary, in the beginning people made smaller infrared telescopes in space. Spectroscopy is a very important part of the job of these telescopes, and more they also do coronagraphy to see planets. You have to dim the stars somehow, and that's done with these coronagraphs, which is very high tech. Because normally you don't just shade the star in a simple way, but a very complicated quantum mechanic type way. The orbits are partly sun-synchronous and partly on Lagrange points. Also, one satellite was also in the L5 point, I think, but many are in the L2 point behind the Earth. And they most of the time have to catch some sunlight, but they're still in the shade of the Earth, which is quite a difficult thing to do. But it's a lot easier than in the Earth orbit, because in the Earth orbit they tend to heat up and cool down, and this is not good for the satellite. So L2 is a good place to be, actually. The sensors grew a lot larger. In the beginning they were very small with only a couple of pixels, and now the sensor of James Webb is really, really large. And often they combine wavelengths near infrared for high resolution, or even visual for high resolution applications, and then far infrared for low temperature applications. Something that interests me a lot is if it's possible to find trans-Neptunian objects, but some source said they are too cold to be detected at the moment. And near infrared is relatively easy to build, whereas far infrared is a lot harder to cool and needs innovative designs and techniques. And there's also a tendency from Ritchey Chretien to Korsch telescopes. On the Earth you can do even more sophisticated designs, but a Korsch telescope is already very, very sophisticated because it has a flat image but no coma whatsoever, which is the problem in Ritchey Chretien telescopes. They also have flat images but some coma at the periphery of the image. Larger telescopes would be possible in principle. These days you could start them with a starship, actually, and make up to 8 meters telescopes. So this unfolding process from the James Webb telescope wouldn't be necessary anymore. But the cooling is always an issue that has to be planned carefully. Actually, James Webb telescope is a step forward in that regard because it recycles the coolants. And thank you for the attention.